Hi, everyone. So this is a joint work with Vijay Vazirani, who is at UC Irvine. So today I'm going to talk about perfect matchings in an undirected graph. So it's just a set of edges, which is for which every vertex is incident to one edge. And the type of algorithmic questions you can ask about perfect matchings, I've categorized them into roughly 3 categories: decision problems, whether or not the graph has a perfect matching; search problem, which is the topic of this talk, which is to find the perfect matching and output it if it exists; and there's also counting, which asks how many perfect matchings there are. Okay? So we are mostly going to be focused on the search problem. The model of computation we are considering is the NC model for the parallel RAM computational model. So in this model, you have polynomially many processors. It's a little bit of an unrealistic expectation to have in practice, but this is a complexity model. So you have polynomially many processors, polynomial in the input size, and these all have access to a shared memory, and you want your algorithm to run in polylogarithmic in the input size. Okay? So whether or not you have access to randomization actually makes quite a big difference in designing algorithms. So there is the deterministic variant, which is just NC, and there's also the randomized variant, which is called RNC. So what is known about perfect matching and this parallel model of computation? It was one of the beautiful gems of computer science that the decision problem can be solved in randomized NC. This is basically by a reduction to polynomial identity testing. Okay? Some years later, the search problem got solved. And 1 year later, there was another method which relied on this famous isolation lemma, which again solved the search problem. And over the last few years, there has been a renewed interest in these types of problems because people found almost NC algorithms which don't use any randomization. First, there was this result of Fener-Gurger and Thieref, which basically showed that search in bipartite graphs, or the decision version was open as well, search or decision was in quasi-NC. So in quasi-NC, the only difference is that you want the running time to be polylogarithmic, and you allow the number of processors to be quasi-polynomial instead of polynomial. Okay? So then 1 year later, this was generalized to arbitrary graphs, not necessarily bipartite. So what is special about planar graphs, which is the topic of this talk? So in general, these 3 problems, decision, search, and counting, are perceived to be in the increasing order of difficulty. That's because decision can be easily reduced to search or counting. And for general graphs, counting is sharply hard, while decision is a polynomial time or even in RNC. Okay? But planar graphs are a curious case because of a very beautiful algorithm which allows you to count the number of perfect matchings, even in NC, without using any randomization. I'm going to talk about it a little bit more. So this table has had an empty slot over here. So we knew how to count, which implied that we knew how to solve the decision problem, but we didn't know how to find the perfect matching in NC. So this result, which allows you to count perfect matchings in planar graphs, is due to Castellane, who basically reduced the problem of counting to solving a determinant or computing a determinant. And then some years later, Shanky showed that you can compute determinants in NC. Okay? So yeah, so the search problem was open. There is a special case of the search problem where you are not just looking at planar graphs, but bipartite planar graphs. So for this special case, the search problem was solved by Miller and Naur first. And some years later, Mahajan and Varadarajan gave a new algorithm for bipartite planar graphs, which also generalized to bounded genus graphs. And our algorithm is heavily inspired by the algorithm of Mahajan and Varadarajan. So I'm going to talk about it a bit more. So this is our main result, that we basically answer the question mark by saying that there is an NC algorithm. And I should mention that there was an independent result showing the same thing by Sankovsky. Okay, so in the remaining time, I want to give you some elements of the algorithm. Okay, so why are planar graphs special? Basically, because we can count perfect matchings in them, and this is because of this beautiful reduction by Castellane. So if you look at your graph and you look at your adjacency matrix, if you put signs on the entries of the adjacency matrix, so that for each edge, one of the two is +1 and one of the two is -1, then the determinant of this signed version of the adjacency matrix, also sometimes called the tot matrix, is basically the square of a sum over perfect matchings of ±1. So depending on how you assign signs, each perfect matching gets a sign, and then you have this sign sum squared. Okay? So Polya, who knew this fact, who knew the bipartite version of this fact, asked whether or not we can choose the signs in this adjacency matrix so that all matchings get the same sign. Okay? So if you can do that, you can count the number of perfect matchings by computing the determinant. Okay? And Castellane showed that in planar graphs, you can do this thing. In general graphs, this is not possible. Okay? And then, as I said, Shanky showed that determinant computation can be done in NC. So you just compute the determinant, take the square root, you get the number of perfect matchings. Okay. So how does counting help search? Okay. So for this, I want to go over this algorithm of Mahajan and Varadarajan, who used counting to solve the problem in the bipartite case. Okay. So this is roughly a sketch of what they do. So they consider the perfect matching polytope. So this is in the Euclidean space of dimension, the number of edges. For each perfect matching, you consider the indicator vector, and you take the convex hull. Okay? So they use counting to find a point inside of this polytope. And then they use some tricks to move to lower dimensional faces of this polytope until they basically reach a vertex, which is a perfect matching. Okay? And the only place that they used counting was to find this initial point. Okay? So this initial point that they find is actually the average of all vertices of the perfect matching polytope. And the way to compute it is to take the fraction of matchings that contain any edge E divided by the total number of perfect matchings, and that gives you exactly the coordinates of the average. Okay? So let me go a little bit more into the details. So it's well known that in the bipartite case, the perfect matching polytope is also given by these linear inequalities. So you want the degree of the total number of edges at every vertex to be 1, and xe's to be positive. Okay? So how can you move inside of this polytope? If you have a cycle of even length, you can do this trick where on odd-numbered edges, you subtract epsilon from your point, and on even-numbered edges, you add epsilon. This can be seen to not violate the first type of constraints. So the degree at every edge remains unchanged. Okay? So you can do this until you hit one of these constraints, or basically one of the edges becomes 0. Okay? So of course, if you do this, this is very sequential. It's not suitable for parallel algorithms. So Mahajan and Varadarajan basically use the insight that you can actually do this in parallel for many, many cycles. So if you have a planar graph, you can find roughly omega n edges. There are some caveats. And you can do this operation in parallel for all of these cycles, and you basically remove one edge from each cycle. Okay? So you do this, you clean up the graph in some sense, and then you repeat. So in logarithmically many steps, this algorithm basically finds a perfect matching. Okay? So what's the challenge of using this algorithm in non-bipartite planar graphs? The challenge is that the polytope is much more complicated. There is a new set of constraints which says that for any odd set of vertices, there should be at least one edge going out of it. Okay? So this was not needed in the bipartite case, but this is very much needed in the non-bipartite case. Okay? So these are exponentially many constraints. And now, if you do the same trick as before, if you find a cycle and you try to remove epsilon and add epsilon, now there might be one of these constraints that blocks you. So here an example. Okay? But thankfully, the saving grace is that if one of these constraints is blocking you from doing the trick of adding epsilon and removing epsilon, then this constraint must be tight. And it's a well-known reduction that whenever one of these constraints is tight, you can reduce the size of your problem by shrinking the graph. So if there is a set S for which the total number of outgoing edges is exactly 1, then you can shrink this set S into a single vertex, and your solution remains inside the perfect matching polytope of the shrunk graph. This is because the degree constraint at the new shrunk vertex is satisfied. Okay? And so if you can find a perfect matching in this shrunk graph, there is a way to basically expand this into a perfect matching in the original graph. Okay? So basically, if you do the same cycle trick, now you either lose an edge from your cycle or you find a tight set, which you can shrink. So in either case, you can reduce the size of your graph. But again, the challenge is to do this in parallel. To remove either a lot of edges at the same time or shrink the size of the graph by a lot. Okay? So I won't have time to describe all pieces of the algorithm, but this is an overview of it. So remember that in the bipartite case, we were moving inside the polytope to lower dimensional faces. So we still have to do the same thing, but now this moving is a little bit more tricky, and I'll go over that. So once you move into lower dimensional faces, you have to find these odd sets that you've made tight, right? So that's the second piece of the algorithm. And because you're trying to find many of them, it could possibly be the case that these things intersect in arbitrary ways. So you can shrink each one of them, but not simultaneously. So the third piece is basically a way of uncrossing these tight sets into sets that are in some sense equivalent, which you can shrink at the same time. Okay? So I'll basically have only time to go over this piece, but I'll mention a few things about the other ones. Okay? So moving inside the polytope. So what's the challenging thing about it in the non-bipartite case? So in bipartite graphs, the perfect matching polytope actually looks more like this. Okay? So imagine that you have a bunch of cycles that you found, and you're trying to do the cycle trick on them in parallel. So they roughly correspond to moving inside the polytope in many directions. I've shown them here in these two yellow arrows. Okay? So the thing about bipartite graphs is that each of these moves interacts with different set of constraints. Okay? Because the cycles are edge disjoint. Okay? So if you basically do this move and you remain inside the polytope, and if you do this move and you remain inside the polytope, you can do the addition of the two moves and still remain inside the polytope. Okay? So this allows you to do this in parallel for bipartite graphs. But then in non-bipartite graphs, the situation is more complicated. The polytope looks more like this. Okay? So this is like one of the constraints coming from the odd sets. So now if you do the parallel moves, you might actually go outside the polytope. Okay? So here is a picture of this. There is an odd set which is interacting with two different even cycles. So each one of them is allowed to move by up to some epsilon, but both of them cannot move by the same epsilon at the same time. Okay. So the solution we have to this is we basically want to find tight sets or tight constraints blocking all our moves. We don't want to necessarily move all the way. Okay? So in this picture, we don't want to move in the addition of these two yellow arrows, but we want to be at a point where no more moves parallel to these arrows are possible. Okay? So to do that, what we did was we find a weight vector. So this is a weight vector on the edges, which has a negative dot product with each of our moves. Okay, so if you draw the perpendicular hyperplane, all of the moves are on one side of this hyperplane. So now if you find a minimizer of w dot x, such as this point, then it's not possible to do any of our moves anymore for this point x. Okay? Because if you could still decrease the weight. And finding this weight vector is actually very easy. For each cycle, you basically set the weight of all edges to 0 except one of them to something either positive or negative, depending on which side you want. Yeah, so this is easy to satisfy with 0, 1 weight vectors. And then the insight is that if you have a weight vector whose entries are integers which are polynomially bounded, then you can basically do the same thing as we were doing for the unweighted case and find the point inside the face minimizing this weight vector. Okay? So this is exactly the same as before, except now you want to count the number of min-weight perfect matchings. Okay? So you count the number of min-weight perfect matchings containing each edge E, divide that by the total number of min-weight perfect matchings, and that gives you the point. And roughly what you have to do to the sign adjacency matrix to be able to do this is to put a univariate polynomial inside of each entry and compute this polynomial in terms of this T. Okay. All right, so that's about moving in the polytope. So to find tight odd sets, the main idea we have is it's well known that if you are able to compute Gomori-Hu trees in your graph, then you can find the minimum odd cuts, which allows us to find these tight sets. So we show how to find Gomori-Hu trees in NC for planar graphs by a reduction to ST max flow. Okay. And then for uncrossing, we just had to come up with some new combinatorial insights on the structure of uncrossing, which allowed us to do uncrossing in parallel. I unfortunately won't have too much time to go into the details of that. So let me conclude. So we showed that perfect matching in planar graphs can be found in NC. So this actually extends to finding the minimum weight perfect matching as long as your weights are polynomially bounded and integral. This also extends to bounded genus graphs because counting can also be extended to bounded genus graphs. Recently there was a result by Epstein and Vazirani who showed that for a slightly more general class of one crossing minor free graphs, you can still find the perfect matching in NC. Now, I think the main there are a few open questions. One is whether or not you can find maximum cardinality matching. So if your graph doesn't have a perfect matching, can you find one which has the maximum number of edges? And for the special case of bipartite planar graphs, this was recently solved by Sankovsky, but the question remains open for general graphs, for general planar graphs. One other question is about exact matching, also known as red-blue matching. So imagine that your graph, so the edges of your graph are colored into red and blue, and you're looking for perfect matchings which have a given number of red edges. That's exact matching. It's one of the curious cases of, special cases of polynomial identity testing. So we know how to do this in RNC, but we don't even know how to do it in deterministic polynomial time for general graphs. Okay? For planar graphs, we do know how to do it in polynomial time, but the question is, can you do it in NC? So, and of course, the main open question is, can you find always perfect matchings in non-planar graphs as well in NC? Thank you. You do find cycles, but then you only use them to find this weight vector, and then you minimize the weight vector. Yeah. So the technique of Sankovsky basically, so the technique of Sankovsky basically reduces the problem of finding an uncrossed family of tight odd sets to basically finding the minimum weight perfect, or finding the weight of the minimum weight perfect matching. So it's a more direct approach. Rather than going through like finding many tight sets and uncrossing them, he basically finds them in one shot by reduction to minimum weight perfect matching.